Welcome to our comprehensive guide on nozzle dynamics and failure analysis for additive manufacturing. In this video, we'll explore the anatomy of extrusion tips, common failure modes, and practical solutions to ensure your 3D prints are successful every time. Whether you're a hobbyist or a professional, understanding the nozzle's role in the FDM process is crucial for troubleshooting and optimizing your workflow. Let's dive into the heart of the hotend and discover how mastering nozzle dynamics can elevate your printing results. Extrusion tip is the final stage in the FDM printing process, and its internal geometry is key to understanding extrusion rate issues. The melt zone is where solid plastic turns molten, preparing it for extrusion. The orifice, typically 0-point form, balances detail and speed, while the flat tip area, irons the print for a smooth finish. Knowing these parts helps pinpoint problems and improve print quality. Let's break down each section and see how they impact your results. Melt zone is where the magic happens. Solid filament is heated and transformed into a molten state ready for extrusion. If the melt zone isn't functioning properly, you may experience inconsistent flow or clogs. Temperature control is vital here, as too low or too high can cause issues. By monitoring and maintaining optimal melt zone conditions, you can ensure smooth extrusion and reliable prints. Orifice determines the level of detail and speed in your prints. A standard 0-point form orifice is a good balance, but larger or smaller sizes can be chosen based on your needs. The flat tip area, irons the print, smoothing out the layers. Understanding how these parts interact helps you select the right nozzle for your project and troubleshoot extrusion issues. Clogs are a common challenge in 3D printing, and understanding their hierarchy is essential for effective troubleshooting. Full blockages occur when zero plastic exits, often caused by large debris or carbonization inside the melt chamber. Partial clogs lead to underextrusion, resulting in thin walls and weak layer bonding. The atomic fix or cold pull method is a manual technique to remove internal contaminants. Recognizing the type of clog helps you apply the right solution and keep your prints running smoothly. Full blockage means no plastic exits the nozzle, usually due to large debris or high-temperature carbonization inside the melt chamber. This can halt your print entirely and requires immediate attention. Regular maintenance and careful material selection can help prevent these severe clogs. If you encounter a full blockage, disassembly and thorough cleaning are often necessary to restore proper function. Partial clogs are less severe but still problematic. You'll notice plastic curling as it exits, leading to underextrusion, thin walls, and weak layer bonding. These issues can compromise the strength and appearance of your prints. Addressing partial clogs early with cleaning techniques and proper filament handling can prevent bigger problems down the line. The atomic fix, also known as the cold pull method, is a practical solution for removing internal contaminants. By heating and cooling the plastic, you can manually drag out debris from inside the nozzle. This technique is effective for partial clogs and helps maintain consistent extrusion. Regular cold pulls can keep your nozzle clean and extend its lifespan. Nozzle wear is influenced by the materials you use. Hardened steel nozzles like the bamboo 0-point form can last a year with non-abrasive filaments. However, abrasive filaments such as carbon fiber and glow-in-the-dark act like sandpaper on soft brass, causing erosion. Choosing the right nozzle material for your filament type is essential for longevity and consistent performance. Microscopic comparisons show how brass orifices expand with use, especially when printing with abrasive filaments. This erosion can lead to inconsistent extrusion and poor print quality. Hardened steel and ruby tips are designed to withstand these harsh conditions, surviving up to 100 times longer. Investing in durable nozzle materials can save time and money in the long run. Heat creep is a silent jam that occurs when thermal energy travels up into the cold zone, melting filament prematurely and causing a solid plug to form in the heat break. Primary drivers include a failing hotend cooling fan, excessive retractions, and high ambient temperatures. Recognizing heat creep symptoms and addressing root causes can prevent unexpected print failures. Steel nozzles often require higher temperatures, typically plus 5 degrees C to plus 10 degrees C more than brass, to achieve similar performance due to lower thermal conductivity. This adjustment ensures proper melting and extrusion. Understanding the differences between nozzle materials helps you fine-tune your settings for optimal results. Calibrating the first layer is crucial for print success. The Z-offset paradox highlights the importance of nozzle distance. Too close creates backpressure and potential clogs, while too far leads to poor adhesion. The standard 0-point tomb gap, often tested with paper, helps achieve the right balance. Proper calibration ensures strong adhesion and prevents common extrusion issues. Innovations like CHT, core heat technology, and Bondtech nozzles are changing the game. Standard nozzles melt plastic from the outside in, but CHT splits the filament into 3 paths, increasing melt capacity by 50%. This allows for faster printing without temperature spikes and higher volumetric flow, especially with larger nozzles. Adopting advanced nozzle technology can boost productivity and print quality. Consistent maintenance is key to preventing nozzle failures. Wipe the nozzle tip after every print to avoid carbon buildup. Every 50 hours, check the nozzle orifice diameter for wear. When changing materials, always perform a purge at the higher material's temperature. Following these simple steps can extend nozzle life and ensure reliable extrusion.